Uh, okay, today it appears to be a full house. They seem to be missing. Okay, so till the last meeting, we have actually covered from the evolution to the materials and to the loadings. We have understood, at least got introduced to the concept how the loadings are decided, what is characteristic load and what is a considered load, and how do we define uh, random loads, how do we define the non-random loads, things like that. We have understood that. Now we will move on to the next aspects of our the bridges, which are related to uh, joints. That is the bridge joints. We'll understand what are the different types of joints, and then we will move on subsequently following to modeling, design, analysis, and modeling, analysis, and final design. That's how we are progressing. So we have started with the development, as I re-summarize, evolution, then the loading, the different types of loading, what kinds of there, what are the classification. Then from the definition of loading, we moved on to understanding how these loadings have been derived, what do you mean by characteristic loading, and what are and things like that. Now we move to bridge joints. So let me start by sharing my window. Please let me know if you are able to see my slide. Yeah. Okay, fine. So we start with the bridge joints. Now, what exactly are bridge junctions? Okay. So when we see, we have uh, basically we summarize our five components of the bridge: the superstructure, the bearing, substructure, foundation, and the soil. So one of the first places where we can think of a joint is between the superstructure and the substructure, junction. We also have a junction between substructure and the foundation, and we don't call the interface between foundation and soil as a junction, we call it as an interface. So the most important junction is essentially where a superstructure joins the substructure. In the transverse direction, we can introduce junction even within the substructure if you have a portal structure like this, and therefore so we can have junctions in a variety of situations. So we should understand what controls our decision making, what are the different types, etc. Okay, so we have another type of junction in the longitudinal section, which is a junction between one deck and the other deck. Then there's a junction between superstructure and substructure, a junction between the deck and the abutment. So these are all we can look at as a junction. So what aspect of these junctions are important to us? Let us move forward. So there are different types of junctions possible. So you have slab bridges where only one junction is there. You have girder and slab bridges where the junction is defined through multiple interfaces between the girder. You have box girder with a limited. You have integral bridges where you have junctions defined in a slightly different fashion. You also have a junction defined for truss bridges, which are there's a overall junction, external junction, and the internal junctions. And then we have arch bridges where we have again a junction between the foundation and the arch. And in cable state, we have a lot more other types of junctions between the cables and the deck, and in the suspension between suspenders and the cables, and then the suspenders and the deck. So we have a junctions at number of places. And what is the purpose of these junctions? What role do they play in the behavior, load transfer, or otherwise of a bridge structure, right? So we can have a junction when we have a multi-span. We have a junction in which discontinuous we have deck, so there is no junction between deck and deck. Or we can have a continuous deck wherein we have a movement possible allowed in the end. Or we can have a suspended span and a cantilever, as you can see here. This kind of an arrangement is not very common nowadays, but in the past it used to be a fairly common feature in long span structures. Now, we have the junction between superstructure and substructure. We could have an integral. Integral means a deck and the substructure in which there is a continuity for force transfer of all types, whether it is shear, bending, torsion, displacements, etc. Or you can have a rested on substructure wherein the superstructure directly rests on substructure, or you can have a superstructure rested on bearings. This generally, the rested on substructure is a phenomena which we see less and less and generally reserved for very small spans. When I say small span, in the past it used to be done for anything up to 20 meters, but today we rarely use it. We tend to, when for small span, we tend to move towards integral solution because each one of them is an unknown performance criteria that comes into picture. And the bearing is generally, we do it for spans which are longer than 25, 20, 25, 30 meters. We always have a rested on bearing. And if the span becomes very large, then for various reasons, we go back to the integral or to the bearing. That's also possible for large span, depending upon the circumstances and a specific design situation. Now, after this, we have understood what the junctions are. We should understand what are bridge breathing units. Bridge breathing units are what we will next understand. What are this concept and what is it that we are actually talking about? So let us take a look at understand the basics of thermal. Imagine there is a bar which is restrained for deformation at the two ends, and there is a neutral position when temperature is equal to T naught. It is at this neutral, there is no stress. The question now is that what happens when the temperature goes below T naught? Okay, what happens when the temperature goes below T naught? Then what happens is, due to the restraint at the end, tension force develops in the axial bar. And when the temperature T grows greater than T naught, then compression force appears in the bar. So therefore, the question is, what is good for us? Do we maintain it at T naught? Do we maintain it as a neutral position, no stress? Do we allow tensile forces to appear? Do we allow compression forces to appear, etc.? These are the questions that are to be answered when you think in terms of bridge junctions and the ability of these junctions to breathe. That is how the bridge breathing unit concept comes into picture. So that was the situation which you saw with restrained bars. So when we have a restraint here. Now, on the other hand, if we had an unrestrained bar, that means the bar fixed in and there is a neutral position T naught, then what happens is, if the bar temperature becomes less than T naught, there is still no tension. There is still no tension, but there is a change in the length of the bar. So if you take a look at contrast this situation, the length of the bar doesn't change, but an internal tensile forces appear when temperature drops, and the length of the bar does not change, and an internal compression force appears when the temperature goes up. But on the other hand, in an unrestrained bar, what happens is, when the temperature goes down, you end up having no tension, but there is a change in the length of the bar. And when the temperature goes up, there is no compression, but there is an extension of the bar. And this is the price you may have to pay when you allow the structure to breathe. When you allow the structure to breathe. What do you mean by breathe? If the temperature rises or falls, you should have no forces that develop in the structure, but then it will have to have an ability to deform. You must build in the deformability in your structure, then only you will have what is called as a no stress condition right through. And this is what is the first concept that you need to understand, that what is a breathing unit, up to what you are allowing the structure to deform or to expand and contract. In as much as the way our lungs expand and contract and we breathe, similarly the structure will expand and contract. depending upon the temperature, and that decision is an important decision for all of you to understand as a bridge engineer. Now, that was in one dimension. Then what happens when it comes to a plate? So let us say we have a neutral position at T equal to T naught, and if there is a rise in temperature and a fall in temperature. So and we have described it as a restrained plate. That means there is a restraint all around. And when the temperature drops from T to T naught, there is no deformation, but there is a tensile force that will appear in the plate. And similarly, when the temperature rises, there is no deformation, but there is a compression force developed in the plate. This is the situation when you have a plate that is restrained from deformation. Now comes a question, when you have an unrestrained plate, that means your plate is unrestrained in a neutral position. When T is equal to T naught, there is no stress and there is no deformation. If you, on the other hand, you have a drop in temperature, the plate shortens in both directions. The plate shortens in both directions. No tensile forces are created. Why? Because it's an unrestrained plate. And similarly, when the temperature rises, the plate expands in both directions, but no compressive force develops in the plate. This is because of unrestrained plate. So that means you have concept called, you have to understand the concept of restrained and unrestrained. So what is restrained? Restrained to deformation, and unrestrained means no restraint to deformation. So depending upon this situation, either one of them will happen. What will happen? If there is a restraint, forces will appear, and if there is unrestrained, deformation will appear. So one thing you have to understand, one or the other you have to cater for in all your design process, right? Now, which is a better bridge? Now this is where it's a question time. You have an unrestrained situation and a restrained situation. The question that I have to ask all of you, which is a better position as far as the bridge is concerned? Should you restrain the deformation, or should you allow for unrestrained deformation? I want you to participate in it quickly. Yeah. Unrestrained. Okay. What about quickly? What others? Everybody can, you have to express your views. Next. Praful. I will call out the name as I see it on the screen. Which is better for bridges?
The unrestrained one.
Unrestrained. What about Mini? Shrutimol?
Unrestrained, sir.
Shreya?
The unrestrained.
Helen? Yes, Milan? He's gone to sleep. Bharat?
Unrestrained.
Sujit?
The unrestrained.
Bhadarni?
Sir, partially restrained.
Want to sit on the fence? Okay, we'll convert the fence into a cutting edge sword. Then let's see how long you will sit on it. Okay, Nayana?
Unrestrained, sir.
Unrestrained. Okay, and Vishal? Okay, Vishal is also not there. Now I'll ask you a question. You all chose unrestrained. So I have a question. Let us say I have a 400-meter long bridge. So should I have restrained or unrestrained? All of you who chose unrestrained, now my question is, I have a 400-meter long bridge. Should I have restrained or unrestrained? Why the silence now? Nobody wants to take a position. Okay, then alternative question. Why do you want unrestrained? No stress accumulation. That means Sujit is strongly against integral bridges. No? I can show you an example of 150 meter span integral bridge. Okay, so others still want to decide that they will always have unrestrained bridge deck. So can somebody tell as to when I will have, when a restrained one is preferable? I would like you to get prepared to answer the question in a more engineering term. When the substructure becomes more and more flexible. Not long. Not long. I can have a 30 meter pier, but if I give you a 6 meter by 6 meter pier size, it is tall. By your logic, 30 meter is tall, no? So it is not a question of height. It's a question of flexibility. That's why I want all of you to be clear which phenomena is important. Not visually, not at the layman term, tall pier. Let's say use correct. So if it is a flexible pier, you might go for restrained bridges, right? So therefore, the question is whether which is better, restrained or unrestrained, depends upon the magnitude of the deformation and the magnitude of the force that it causes in the superstructure. Yes or no? Now, I would like all of you to do a calculation on a very typical bridge, very typical bridge. Let us say you have a uh, 25 meter span. Just as an example, a 25 meter span, and let us say the bridge deck is around 12 meters wide, and let us say the area of cross section of the bridge is about 8 square meters, typically 0.65 in that range of an average. So 8 square meters, let us say, is the cross sectional area of the bridge. Length of the span of the bridge is one single span is 25 meters, and let us say the grade of the concrete is what should we choose? Say 25 M25, because square root of 25 is easy to calculate. So it is 5 into 5,000. 5,000 into 5, 25,000 MPa will be the modulus of elasticity, right? So if somebody can calculate for me, what will be the force generated if we restrain this 25 meter span bridge for a rise in temperature of 1 degree centigrade? Somebody do the calculation for me quickly. "25 meter span, 8 meter cross sectional area, 25 MPa, 25,000, 2,000, 5,000 to 25,000 MPa as modulus of elasticity and 1 degree rise in temperature. Assuming that alpha is 12 into 10 to the power minus 6. Do you recall this number when we did the temperature loading? Coefficient of thermal expansion. So let us say it's a linear bridge, that's the area. Can somebody do, is anybody doing the calculation? I want you to tell what will be the force if it is a restrained arrangement. What happened? People are not able to do. Only you are doing. What about others? I have finished my calculation. Don't tell me others are not sure how to calculate. Ah,
2,400 kilonewton.
240 tons. So now my question to you is, see, I have told you 8 square meter, 12 meter wide deck. Okay. So, or even 15 meter wide deck, 15 meter by 8 is a 0.55 square, very common cross section. So such a cross section, when the temperature rises by 1 degree, the restraint force is 240 tons. Do you think you can create a bearing? Now imagine that you have to design for a, say for example, 20-degree rise in temperature, directly proportion, right? So it will be how much tons? 240 into 20, 4,800, 5,000 tons due to a 20-degree rise in temperature. So do you think you can restrain it? Can you actually do a restraint design? If on the assuming that the foundations are infinitely rigid, is it possible to restrain such a superstructure? Yes or no? So therefore, this is the one fundamental reason all our bridges have arrangements for deformation. You may like to, even when we don't provide a bearing and we provide only what you call it as a tar paper separator for small spans, even if assuming that for such a cross section also you provided something like that, then what will happen is that 8 into 25, which is 200 cubic meters into 2.5, which is about 500 ton is the weight, assuming another 40 tons, 50 tons superimposed dead load and another 100 tons live load. Altogether, you will have about 700 tons of gravity load divided into 350. Even if you provide a material with a very large friction coefficient of 0.5, it will produce a reaction in the superstructure, I mean force in the superstructure, or rather it will limit the force in the superstructure and the force in the substructure 175 tons. Whereas 1 degree, because that will be dependent only on the friction coefficient and the weight. So therefore, it's practically impossible to provide for a 100% restraint because of this is the magnitude of the force that it will create. So therefore, it becomes very important. Now imagine that quite often when you travel on the bridges and you see the expansion joints are clogged with dust. It doesn't matter because 1 degree rise in temperature, this dust will simply get thrown away. It will get crushed because it will not stand there. So therefore, clogged expansion joints are not such a great problem for preventing the movement of the deck because the magnitude of force is so huge. These small dust particles will do nothing about it. Okay, so it is very important to understand that restrained bridges are very, very difficult to design and very, very difficult to achieve. So there is no such thing as a purely 100% restraint. Similarly, there is no such thing as purely unrestrained bridges because This there is no space in this universe where there is nothing called friction available. Whenever there is a movement, and if it is a bridge, means it will be supported, at least simply supported on both ends. So when the relative movement takes place, what will appear automatically? Frictional force, because frictional force is a force that appears every time to oppose any movement, any motion. Even the tendency to have the motion, it will be opposing. Therefore, strictly speaking, there is no pure unrestrained movement and there is no pure restrained arrangement. Okay. Now, we have a choice. Say when we have a 3-span bridge like that, we have a choice that we can put a flexible abutment of this nature, and for which when we do the loading, you will realize that you will find the deck will be deforming, along with it the substructure is deforming, and the temperature loading will say it will push out the pier, as you can see in the deflection of the pier here. Okay, so the zero movement point kinds of comes in the middle. So you have even gravity loads causing you longitudinal movements in the deck. Even gravity, as you can see from the self weight, as long as you have a deck which is monolithically connected to the superstructure. So therefore, you cannot ignore the longitudinal deformation of the bridge, and that important activity is covered by the arrangement which we call the arrangement at the joint. So we know all the types, we recap all the types of force loads from dead load to pre-stressing load and displacement load from temperature to earthquake load. So all of them need to be accommodated in some form of deformation or other, right? So therefore we come to the important concept of movement at the bearing. So this is a classical example of when the bridge superstructure relative movement between superstructure and substructure. If there is a uniform temperature rise, then you will find that the support at the other end, if this end is pinned and the other one is roller, this is a conceptual idea. The support point moves along with the superstructure. Now, why is it the other way around doesn't happen? Because of the fact that we have connected it and we are making sure that the movement happens relatively, the superstructure moves, and that is the only one that is likely to move. Substructure and foundation are less likely to have any impact of the thermal rise and fall of the temperature. Now, that is for the uniform one. And when you have a differential temperature, what do you mean by differential temperature? The top of the deck being hotter than the bottom of the deck, then it will hog up. Of course, this picture is drawn somewhat erroneously. It will be somewhere in between the two of them that will happen. And if you have a the top of the deck cooler than the bottom, in which case it will get pulled backward. So deformation is caused not only by uniform temperature, it is also caused by differential temperature. This you must keep in mind. It is also caused, the longitudinal displacement, it is also caused by gravity loads. If I had a vertical load, you can imagine that it will also end up having a curvature exactly like this, in which case there will be a longitudinal movement in the between the superstructure and the substructure. Now, all our process right now is to understand what are the phenomena that cause the relative displacement between superstructure and substructure, and how do we handle it, and what's the best way to do it. There is no question of, I shouldn't use the best, what is the most ideal one to do it, depending upon the individual situation. Okay, so if you now we come back to we have already established that the need freedom to move, it must be built into your superstructure in one form or other. So initially we will look at it as if the substructure has no role to play in making that. We will look at it only as a bearing. Okay, so imagine that we have a bridge deck. This is the old style rocker bearings at the two ends, and this is the roller bearing in the two end. So what does this do? This does not permit any movement in the transverse direction. On the other, it permits only displacement in the longitudinal direction. Say we have an X and Y direction. Okay. So for both the force loading as well as for displacement loading, this is the only displacement possible in the old classical rocker and roller arrangement. But if on the other hand, we go to a more modern bearing arrangement, where we have a fully restrained bearing here, a transversely guided bearing here, a longitudinally guided bearing here, and a fully free bearing here. What does this do? It allows displacement both in the transverse and in the longitudinal direction. So this offers a greater choice of freedom. When it offers greater choice of freedom, what does it mean? That it has got less restraint. This has freedom in the longitudinal direction, but restraint in the transverse direction, right? So it cannot breathe. It cannot breathe along y-axis, and this can breathe along both x and y direction. This is what is the classical difference between the old. When I mean old tradition, nowadays you will rarely find this situation used anywhere. We have understood the breathability and the internal stresses that it creates little better. So invariably we go for this type of bearing arrangement, the bearing arrangement that allows at the joints breathing in both x and y direction, right? And this is a designer's error in those days, primarily because of the fact that we didn't have the kind of bearing, they didn't have the technology to create this. But today, this has become the designer's choice. That was an error, but we accepted it in the olden days for a simple reason that our bridge decks were narrower. We can't afford that choice anymore. We cannot make this erroneous choice. We have to go to the designer's choice because modern bridge decks are much wider than what we used to design in the olden days. Okay. Now, if you have to understand the movement at bearings, you have to understand few special cases. One such special case is when we do two bearings which are very close to each other, and we have a long span in between. This kind of an articulation is very bad choice. It's an extremely bad choice because of the fact that under the movement of this vehicle, there is an uplift that is going to come at the bearing. Okay, this bearing typically bearings are incapable of resisting uplift force. Now, generally, please note the word generally. That means in 99% of the case, the bearings are not capable. However, in some special circumstances where you do want to take care of the uplift, there are special arrangements, but they all come with a price. When you provide for resisting uplift forces, then you will lose some other freedom. So we'll understand that as a special case. But for the time being, you please understand very clearly, uplifted supports are not acceptable. What does it mean? That you shall not have two bearings which are supposed to resist compression so close to each other next to a large span, so that the positioning of the live load actually causes a physical uplift. This kind of a bearing arrangement you should avoid. That means such joints, bridge joints, are absolutely to be avoided. Okay, this will be classically classified under designer's error if you do it. Don't get tempted into it to provide two rows of bearings at any support which is with a continuous structure. Don't get tempted to it. Even if you have to design a larger capacity bearing, provide for a single row of bearing. Okay. Now, in a special cases of the bearing, you have another problem. This is when you end up in a skew bridge. So this is conceptually a skew bridge supported on the two short edges. Then what happens is that you end up having a possibility of liftoff at these acute angle corner. Now the question comes, why does this happen? This happens from the behavior of the slab itself. When you place the load tends to travel by the shortest path. So this becomes the shortest path, and therefore, and in the transverse direction, it tends to occupy deflected shape like that. So both these corners tend to have the possibility of liftoff. Now, which means what? When you have a skew bridge and when your ratio plus remember one thing, when you talk about skew bridge, just because it is of this nature, it cannot become a skew deck per se. It depends upon the ratio of this span to this width. That is something parameter which is a slab behavior. We'll understand it separately in some other day, but rest assured that if it is a slab bridge, slab arrangement in which you have it is on skew, these acute angle corners always suffer from the possibility of liftoff. So you have to take care of it in the bearing articulation arrangement. Now this is critically important if you are ever getting to work in bridges in which the skew angles are say more than 30 degrees and the aspect ratio of span to width are really adverse. Okay, so the acute corners uplift or support is not acceptable. So then comes the question, if we have a same span but different skews, then what happens is the load path, the load spanning path becomes this green and the rest of it will not participate so much in the uplift, I mean in the load carrying path. So what will happen is significantly larger longitudinal stresses and forces will happen here, and therefore deflection will be larger here and these deflections will be smaller here, in which case what will happen is the zone of uplift will be larger. This is the potential zone of uplift. And if on the other hand, the width is the same, the span is the same, but the skew angle is less, then what happens is the normal load path with near uniform deflection from width to width increases and the uplift points reduce. So then the question comes, this is what I wanted to make the point to you, that it is dependent upon both the skew length, skew angle and the width of the deck. In this arrangement, on the other hand, let us say the deck was narrower. Okay, let us say I will just come out of it and we'll do some editing here. Let us say the deck was narrower and we didn't have this and we had this. If this was the deck width, then you realize that for the same loading area, the amount of uplift zone is reduced. Okay. So it is a matter of deck width also, and in the same thing, if on the same skew the deck width was increased, so the uplift area will also keep changing accordingly. So you have for skew bridges, the amount of uplift zone will depend upon the span as well as on the skew angle that we and the deck width. Okay, so if you have a larger skew, you have more potential for uplift, and if you have a smaller skew, then you have some other awkward situation which many people you might have seen, but you should avoid for sure. If you have a wide deck, you should avoid these kind. There's a temptation to say that I will use 3 bearings. How many of you have seen such a bearing arrangement? How many of you have seen a wide deck in which you have 3 rows of bearing? Yeah? Anybody? Nobody? It was the original proposal in Dwarka Expressway that we have a bridge deck wide with 3 rows of bearing, and the question was, in the case of as you have seen a few slides back, the impact of the thermal gradient, when the top surface becomes hotter, the A deck tends to hog in a similar fashion. In this case, when the deck becomes hotter than this, it will tend to hog this way, in which case what will happen is you will have an unseating of the bearing, unseating from the bearing, and therefore every likelihood that this bearing is practically ineffective and most of the loads will be on this side. And it will be vice versa. In the case of a temperature fall, most of the load will come to this bearing and this will get uplifted because then it will sag the other way around. Now, that is where the question is, when you have wide deck, as far as is possible, choose your deck support carefully so that you don't have the bearing uplift of this nature. So it is also, it may be good practice to in fact go for a bearing which is something like this, an indirect support. It might be worthwhile going for these two, the blue type of bearing, instead of, and remove the 3 red, so that you always have the loads on the bearing. But what it would mean is maybe at the bearing support you need to strengthen your bridge deck. So quite often your choice of the bearings will depend on being very judicious. So differential temperature will lead to unseating from the bearing. So this special case, the joint also you need to be very careful about. The third case of special, yeah, somebody is asking question. Yeah. The question, pier cap, see, that is what we have. How much lift off do you think you need to remove the load from the bearing? You will require, typically, let us say if you are a potent PTFE type of bearing, 1 millimeter is enough. But if there is a 1 millimeter deflection, will it touch? Your no bearing is less than 100 mm thick. So 1 millimeter will not touch. This will. This is an exaggerated deflection. This is just to say that lift off is possible. This is just to tell you that this behavior exists. But this behavior is not going to be 50 millimeter, 100 millimeter. In a typical wide deck, it might be 3-4 millimeter, but that is enough to uplift the load from the central bearing. But a 2 or 3 millimeter is not enough. If it was blue was the choice, 2 or 3 millimeter dipping of this will not lead to it touching the girder, because this bearing will not be 5 millimeter thick, no. This bearing will also be 100-120 millimeter thick. So it will not touch from that point. That's the that you need not worry about that. Okay. Now, the third special thing that you need to be careful about is when you're talking about when you're seated on a bridges on skew, right? So the example that you are seeing here is a skew bridge, which the span which is crossing the road is integral, and then you have a what do you call it, a simply supported bridge deck coming and sitting on top of it. What ended up having a problem was that when there was a earthquake and then there was a lateral shaking of the bridge deck, you found that when they provided the bearing articulation they have done, that is the fully fixed, guided and things like that, it ended up having, ended up having was that the deformation all got accentuated in one place, it got unseated and the whole deck fell down. You can see the deck lying in the bottom. This bridge is intact, this spans are intact, including surprisingly few vehicles which has stopped in time and didn't move when the earthquake came, and they survived instead of falling down. So when you are doing the bearing articulation for skew, it is very important, as far as is possible. I am not saying it is always possible. As far as is possible, avoid developing a skew layout. There are ways and means in which you can change this deck behavior and foundation behavior to avoid skew layout. Try to go as far as possible to the right layout, as far as possible. I am cautiously using the word, because tomorrow you shouldn't go back and say, I told you to not to do skew bridges at all. But if you are doing skew bridges, make sure that your arrangement is such that you don't have these unusual displacement issues which plague all the skew bridge deck, which can lead to unseating. You have an unseating in this case due to the fact that lateral shaking will lead to what do you call it coming and touching somewhere and the whole bridge deck going in a skew, and that completely getting unseated. And these are especially this location where the bridge deck span is coming and sitting on top of it. When it got unseated, it became pure cantilever. Then the strength of the deck also vanished, and the whole deck cracked and fell down. So when you are doing skew bridges, be careful, but more importantly, as far as is possible, avoid skew. What did I say? What did I say? As far as is possible, avoid skew layout for the bridge decks. Right. Now, let's understand the question. So when we have type of bearing, the symbol normally used when you see a dot, it means it's a fixed bearing. What does it mean? It means that it does not permit relative displacement between the deck and the supporting substructure in both directions. It does not permit. And if you see a symbol like this, it says it permits movement in both directions. And if you see something like this, it permits in the direction of the arrows. So typically a bridge deck is laid out this way. You have one fixed and one, this is what in common language this may be called as a transversely guided, and this will be called the longitudinally guided, and this will be called as a free bearing. So this is a typical straight bridge layout, which when it comes to skew, we do the same thing with some arrangement of this nature, transversely guided and the longitudinally guided, right? Now there are two types of arrangement that we normally talk in terms for continuous bridges. We have one layout is called the polar radiating bearing arrangement. That means the bearings are aligned along and perpendicular to the radian lines from the restraint bearing. So let us say these are different piers, and in this 1, 2, 3, 4 span continuous structure, you have only one restraint bearing. What does restraint bearing mean? Recall, it doesn't permit movement in both x and y direction. And you have a free bearing here. You have a longitudinal guided bearing, longitudinal guided bearing, longitudinal guided, and all these other 3, 4 support. All of them are pointing towards the restraint bearing, and that is free bearing. So it doesn't matter how you lay out. So this kind of a arrangement is called as a polar radiating bearing arrangement. This is one possible option for a curved continuous bridge. But quite often, the other alternative one that is commonly seen is also a circular curved and straight. For circular curved and straight bridges, you get what is called as a tangent bearing system. So you have one fixed bearing and all the guided bearings are tangent to the curvature. They are tangent to the curve. So this is also possible. Now comes the question, which is better? Is the polar radiating system better, or the circular curved or tangent bearing system is better? Yeah. Any views? Polar is better. Why? Why is polar better? Knowing a fact is good, but knowing why the fact is a fact is even better. So why is polar good? Do I need to take a poll again? Why is polar good? Sujit, Sukalyan has said so polar is good. Now I want him to defend his position. Why is polar good? Better than tangent varying? Hit and run not allowed. Hit and defend is allowed. So why is polar arrangement better? Come on. Nobody wants to take a call. Or I'll put the other way around. If you believe the tangential bearing arrangement, somebody come out and say that. Anybody in, let's say, how many in favor of polar radiating? Raise the hand. One by one, you can call out. Sukalyan is in favor of polar. What about the others? Praful? Yes, please. Praful. Shruti?
The polar is better since during thermal stresses will be less.
Okay, so when thermal is important, you say polar is better. So when is tangential better? Never.
No, tangential. That I don't know.
Okay, Shreya?
I think polar is actually depends. I think depends on the
You
arrangement.
defend whatever position you want to take, you defend it. Okay,
if
so you
if we
me.
want
yes,
I think
please.
yeah. I think it depends on the deformations. What kind of in which direction we are looking for the deformation.
Oh, what do you mean by that?
So for the thermal
you generally for all the phenomena we have gone through the list of force deformation, force based loading and deformation based loading. So you know all of them. 10 plus 6. Now by now it must be embedded in your mind.
So for the thermal and the creep, the deformation.
For that, what is good? Yes, you stopped.
So I'm thinking.
See, just remember, you are among friends. So then only you will be able to vocalize. So for that, what is better? Or both of them are okay, equally bad. Okay, we will spare Shreya. We'll move to Bharat. Yes, Bharat, which is better?
I think polar only, sir.
Polar, all circumstances, polar is better. Okay, that's at least why. Okay, we'll spare Bharat continue. Shojit.
Sir, for tangential bearing, it will be easier during construction.
Okay. So one positive side for tangential bearing.
So
but structurally, which is better?
For linear stresses, sir, I think it will be better.
So for what? What will be linear stresses?
Sir, like
So what will be what are linear stresses?
Like, sir, for continuous PSC girders, where
So we are only discussing continuous girders. So you should have chosen tangential boldly. Yes, Bhavadharni, next. The floor is yours. What's your choice?
Hello, sir.
What's your choice? Which is better?
Sir, actually, it depends. Actually,
Depends on what?
The radius, constant curvature, and so and so.
Both of them are constant curvature. Let's not mix too many variables. We'll handle one variable at a time. Both of them are same radius of curvature.
Then tangential bearing system is good.
Better. Okay. So we have about 3 for that. Praful hasn't answered at all. Yes, Nayana, what about you? Which side of the fence? Hello?
Hello.
Yes.
Polar, sir.
Polar is better. Why? Why is polar better? Making a choice, as I told to Sukalyan, it's not enough that you make the choice. You need to know why you make the choice. Okay. Vishal, you still there with us or you left? Hello? Okay. So, let's go back and understand what did we see about the breathing. We are looking at thermal. What happens in the thermal effects? In thermal effects, what are all the dimensions of an object will change if you do thermal rise or fall? Which dimension? All solid objects have X, Y, and Z, 3 axes, right? That's why they are 3-dimensional objects. So, in the case of thermal stresses, which all dimension will get affected? All the 3. Okay, that is as far as thermal. What about shrinkage? No, absolutely not correct. Are you telling me shrinkage takes place only in one direction?
All the direction.
Exactly, all the 3 directions. So now, you know, temperature and shrinkage, they change dimensions in all the 3 directions. So you can call them what? A volumetric change phenomena. Now let's look at other phenomena. When you take the gravity loads, dead load, live load, okay, at this stage, which dimensions will get affected? Creep, pre-stressing, which dimension will get affected? So now, can anybody formulate a rule which is better under what circumstances? I have given you the clues. Now let us see if you can connect the dots.
For longitudinal thing, tangent bearing system and volumetric thing is affecting more means polar radiating system.
So you have summarized it well. Now I'll ask you a question. Do you ever have a bridge where it is completely dominated by one or dominated by the other? Let's be very clear. Temperature and shrinkage you cannot avoid. Can you? No. Especially if you're doing concrete. Especially if you're doing. Let me correct myself. Temperature you cannot avoid if you're doing steel, but if you're doing concrete, temperature and shrinkage, both the phenomena are unavoidable. So that means there's always a volumetric change phenomena causing deformation. But on the other hand, live load is there in all bridge, whether it's concrete or steel. Therefore, a linear deformation behavior is there in all the bridges. Then, as far as creep is concerned, creep is always linked to pre-stress and concrete. And therefore, if it's a concrete bridge with pre-stress, then creep is also a significant deformation phenomena. Then comes the question, therefore, and finally, among all of them, in the linear one, the critical thing, and even in the volumetric one, the critical thing is the radius of curvature. So if you have a sharp radius of curvature, that means if the radius of curvature is small, then quite often you will find that the net forces, not design forces on both substructure and foundation, may be less if you go for polar radiating arrangement. Generally, why I am saying that, but if you go for small radius of curvature, possibly the total length of the bridge also will be small. It's rare for a long bridge to continue on a sharp radius of curvature. If you have a long bridge, generally they tend. So if the radius of curvature is large, then it is better, easier, because as Shojit mentioned that it is construction-wise is easier to go for tangential bearing. Next question, next choice is, if on the other hand, that you all know, if you have done a few designs, you will know how much deformation strain is caused by shrinkage, temperature, creep. When you compare all of them, you find out which causes more strain than in the total. Then that should give you an idea which direction you do. So therefore, either way, in whatever choice you do, whether you do, if you choose polar radiating, then you will get transverse direction forces under the pre-stressing and creep behavior. If you choose tangential bearing system, you will get transverse resultant forces under gravity loads as well as from under temperature and thermal stresses. So there is no situation in any articulation that you can actually avoid stresses, because we have a mixture of loading. The main problem is we have a mixture of loading on all bridge decks. So whether to choose a tangential or whether to choose a polar radiating depends upon which deformation is significant. So for the first time, you are reaching a situation where the choice of bearing depends upon an estimation of deformation. So far, we were all choosing it on the basis of the estimation of the forces. This is the first time you end up choosing it based on the estimation of deformation, right? Then comes a complicated situation. I have a curved one like that, a general curve. Which system of layout should be used? Very difficult to answer. You have a varying deck, you have varying radius, you have change in the direction of curvature, etc. So again, the rule that you have to do is you may end up having to do it on the basis of choice of the magnitude of the forces. So if you have a general continuous in which the radius of curvature is going on changing and you keep doing the tangential bearing system, so it might be favorable from such situation to do that and pay the price for it, make the construction easy and pay the price for it in the design of the substructure and as well as the bearing. Okay. Now, if you have non-straight bridges, generally when you have a volumetric change, they will tend to have a deformation like that. So in that case, what happens is that you if you choose the bearing which is a tangential layout, for this it will be relatively stress-free. But as I told you, it always you pay the price for it in the one which has causes a one-dimensional, one axis based deformation. Then you end up having the lateral forces. All right. Let's take a few simple cases. Say you have a two-span continuous bridges. Then you have a choice. You have a choice wherein fixed bearing here, and you can see as soon as you see this layout of bearing, you will automatically understand that this is a polar radiating arrangement because all the restraint bearings point towards the fixed one. So this is a polar radiating, which means it is good for all the volumetric change type of loading, comfortable for that, right? And in the case of longitudinal effects, also since significant direction of movement in this, so this will suit for that also. So it's not curved, but it's a two-span continuous bridge. Now, in a single bridge, you have possible two choices. You have all the restraint line in this, and you keep the other two force. Is it good or is it bad? You have choice one, bearing choice one. That means I have one fixed, one longitudinally guided, the other two free, versus one fixed, one transversely guided, one longitudinally guided on all three. Between the two of them, which one would you choose? Why? So that is not the only thing. So what? Now my question to you is, generally, which load in the bearing actually governs the design? Other than the vertical load. Which lateral load actually governs design of most bearings? You're looking at this longitudinal force. You say this longitudinal force will be shared. If this longitudinal, but this longitudinal force is caused by multiple things. It can be caused by braking and traction. For the time being, ignore, let us say wind, it's a low wind zone, and it is possible caused by the longitudinal seismic. Correct? And so if that is the case, then what happens in this case, when it comes to transverse bearing, in the arrangement 2, all the transverse seismic forces goes on A. A and C also, correct. So the question is, but there is another phenomena that comes in, that when you have any longitudinal force which is acting at the CG and you have a support reaction here, there's an overall transverse bending moment which will lead to additional lateral loads that are coming into the fixed bearing. Agree or not? Equilibrium cannot be lost, right? The reaction is coming here, the force application is there, there's an eccentricity that's equivalent to this bending moment. This bending moment can only be resisted by a formation of a couple, which has had a reaction in this direction and reaction in this. So therefore, while your force is F, your fixed bearing ends up being designed for F plus an additional in the perpendicular direction. That is another bigger reason why this is not a good bearing arrangement. Your choice was correct, the 2 is correct, but it is not only just that, but this causes an additional unnecessary loading on the bearing. Okay. Whereas in this case, it is an equilibrium. And you will notice that this is equivalent to your tangent type bearing, and this is equivalent to your polar radiating bearing. That's another reason why for simple situation, polar radiating bearings are the one. Other complex one, you take a call. You take a call, sometimes tangents are better for other phenomena. Then you have next situation, you have a tangent bearing arrangement for a skew, and you have a polar radiating arrangement for the right two-span continuous bridge. One important thing about all these bearings are different stiffness and materials. They should never be used on the same pier. That means if you are using this pier, the material of this bearing and this bearing must be the same. It should not be one elastomeric, one metallic, or things like that. This doesn't, when they say stiffness, it doesn't mean that you should always have fixed bearing both. No, what it means is one metallic and one flexible, not permitted at all, not good. Because it's a continuous structure, even in transverse direction, you will end up having a redistribution of loads. Now we have so far looked at the bridge breathing units. Now we'll move to the next unit called the bridge vibration unit. This is related to the displacement connectivity between different components of the bridge. Okay, so if you take a bridge vibration unit, we have simply support span, multiple span simply supported, and a multiple span continuous bridge. Okay, so when the longitudinal movement of the ground takes place, then this blue shade, the mass of all this moves together, and the mass of this pink moves together. So this blue mass together, that means this superstructure, this abutment substructure in this example is one inertial unit. Okay, but in the transverse direction, when you have a pinned bearing and a roller bearing which is a restraining movement in this direction, then for the transverse direction, all of them together is one inertial unit or one bridge vibration unit. So you can say the same bridge, depending upon the direction of the ground shaking, has different inertial mass units. That you have to be very careful about. Why do we need to? This all we'll go towards eventually when we start doing analysis. You will understand what it means to how to define and do that. Okay. Another example we want to see is if you have a multi-span bridge in which each one of them is simple, then you have this as one bridge vibrating unit, this as another vibrating unit for longitudinal shaking, this as one other, this as another, and in the transverse direction, the bridge as a whole is a vibration unit, single vibration unit in the transverse direction. So therefore, and in continuous structure, let us say we have this as an integral and this is the fix to it. These are all integral and this is the roller. Then other than this, all the rest is one vibration when the ground shaking is in the longitudinal direction. And in the transverse direction, as with everything, the whole unit is a single unit for the ground shaking in the transverse direction. Now, for long bridges, if you have multiplan simply supported one, for longitudinal, each one of these piers become the individual vibration unit, and for the shaking in the transverse direction, the other one becomes the whole bridge becomes the transverse vibrational unit. Okay. Now there comes the question. In this case, when do we always have to do in the transverse shaking treat the full bridge as a single vibration unit? Is there any circumstances in which we can avoid it and not do it as a full bridge? Under which circumstances can a long bridge with simply supported span for the transverse direction ground shaking can we avoid treating the full bridge as a single inertial unit? Any circumstances? No, the arrangement is this. Even for this structure itself, for long bridges, is there any circumstances in which we can avoid treating the full bridge unit as a vibration unit, single vibration unit? Don't change the articulation. Then you're changing this breathing arrangement itself. This is the breathing arrangement. This is a long bridge. Logically, in the transverse vibration, the whole bridge acts like a single vibration unit. Is there any circumstances in which, without changing the bearing articulation, that you can avoid doing the full bridge unit as a single vibration unit? From analysis point of view, is there any circumstances? What if I were to say that the bridge is very long, multiple span, very long, and all the piers are of nearly the same stiffness? Have you not done such an analysis? Treating an individual pier in the transverse direction as a vibration unit, single inertial unit. Yes or no? Or have you always done in the transverse direction full bridge as a single inertial mass unit? So you have done it. So what is the assumption behind it? There is an assumption behind it, right? And that assumption is, okay, superstructure is all uniform. Maybe that is one condition that is satisfied. Also another unit, you are saying that the piers are of nearly equal stiffness. So one pier I do, it represents all of them. And the influence of an odd abutment is outside the purview, far away. So I'll treat the abutment alone separately. Haven't you made these assumptions without stating so? So therefore, under certain circumstances, you can simplify your. Remember, every simplification is an approximation. Okay, every simplification is an approximation. So therefore, you can do a single individual universal. Okay, now how many? If you have this arrangement, that means you have a pier, pin roller, pin roller, pin roller. So you have a connection here. So how many bridge breathing units are there in this? In this situation, one condition here of this nature, and another one, what we have done is we make both the pin down one pier and we make this as a 3 pier. So what will be the, how many types of bridge breathing units, vibration units will be there in this? This is something that you work it out for yourself. Okay. Now the issue with the bridge vibration unit is also compounded if you have a skew span. When you have a skew span, the inertial mass distribution is not uniform. When you have a right bridge, if you have a multi-column solution, most of the time your inertial mass is nearly equal for each of these columns supporting it. But if you have a skew, the inertial mass distribution also changes, and therefore the transverse deformation characteristic changes, and it can lead to pounding in one place, unseating in another place. This is one more reason why in seismic zone, try and avoid skew bridges as far as is possible. I'm always saying there might be circumstances wherein you cannot avoid it, but in high seismic zones, please avoid generating skew spans. Try to get right spans as far as is possible. Okay. So it leads to a situation where the inertial mass is here, and let us say this is your what do you call it, the bearing articulation, fixed and tangential guided, and then you will find that because of this issue, there will be a reaction will come from one side, depending whatever be the angle issue, there will be a moment here, couple here. It will lead to non-uniform displacement, and you will find that more inertial mass is locked into one, and the deformations will be twisting like this, and then you will end up having an unseating possibility. Okay. So there are this, we are again discussing two things wherein you have this bearing articulation changed. So each one of them will lead to its own deformation characteristic. You have to be very careful about it when you're analyzing, and you should then only decide which is a better articulation. And the third possibility is polar radiating one, which is good. That's something that is important to choose when you're doing an skew span. But ideally avoid all skews in. Why are we talking about vibration unit? That means somewhere you have a possibility of ground shaking. So we are saying avoid as far as is possible. Wherever reasonably strong earthquake is possible, avoid skew spans. Okay. We will call it a day here, but we will have still time for half an hour for any questions. We will move on to the next part of the bridge joints in the next class, next Friday. But today, enough for the day. You can ask any questions that you have on what you heard today. Today you were introduced to the concept of bridge breathing units and bridge vibrational units. Actually speaking, when the earthquake events happen, the waves that are generated due to energy waves that are generated due to the state change, it has got all the components in all directions, plus the fact that the event happens, say 30-40 kilometers below the ground. And from there, when the energy waves radiate in all directions, it will meet all kinds of strata, like waves in a glass. So you have reflection, refraction, all of those phenomena also happen through these energy waves. So therefore, you have energy waves traveling in all the three directions from the epicenter. So when you come to a bridge location, so it is easy for us to understand longitudinal direction shaking and transverse direction shaking. But also in vertical direction also there is, because of the nature of the waves that are originating from the epicenter. The question happens now, when the bridge deck is subjected to ground acceleration in the vertical direction, the response spectra that has been given to us, which we all generate through the single degree of freedom model, which you remember when we did the understanding of the earthquake load. How do we get? We have a random vibration which peaks, accelegrams are recorded. That accelegram is translated into a design response spectrum, evening out all the irregularities and smoothing it out. That model has been developed for a single degree of freedom, primarily in the lateral direction, with the consideration of the what do you call it, of the flexibility of the pier. Now, when it comes to vertical direction, what happens is, in the vertical direction, your piers are very stiff. You agree? There is no pier flexibility at all, because under axial compression, all columns are very, very strong, unless they have a significant buckling potential, which we don't want to have. Most of our columns will be so proportioned that they will not, because buckling is an instability problem. We will want to avoid that. So it is extremely stiff, which means what? In the vertical direction, your response spectrum will always land in the small time natural period zone, which means the highest SA by G. And that value can be very significant, right? And based on the fact that how much of the energy is distributed in the vertical direction. See, what happens is, when they have observed so many earthquakes, some amount of vertical displacement of soil does take place, but significant amount of soil displacement takes place in horizontal direction. They don't have the data, so they have prescribed an empirical arrangement whereby they say you treat, what's the value now? Take 2/3 of it, right? Your response spectrum is for horizontal. Time period is calculated for vertical on the same response, single degree of freedom, accounting for all the stiffness, but they know that the magnitude of energy that is transmitted in the vertical direction is much smaller than in the transverse direction. So they have given you an empirical formula which just reduces the magnitude of the intensity to 2/3. That's all there is to it. They don't have enough data to tell how much energy is actually being transmitted. Imagine that significant portion of energy is going up and down. Then what also you should see during the earthquake phenomena is ground moving up and down, correct? That has been observed in a very, very limited fashion. It's not that it is not observed, but it's observed in a very limited fashion, and therefore they scale down the effect of it by prescribing 2/3. No. Inertial mass is in it's in both direction. Plus remember one thing. When the earthquake phenomena, what exactly are you analyzing? You are saying that the ground earthquake wave has gone past the structure. It goes in a few seconds. But the structure, after it has absorbed the energy, continues to do free vibration for some more time until the damping takes over and reduces the motion to 0. And in each cycle of vibration, it dissipates the energy that is absorbed. That is why we always say the earthquake force is dependent on the natural period of vibration. Okay, so in the vertical, now imagine that dissipation is purely possible only with the structure in deformation. But when you talk about in vertical direction, if the displacement is in vertical direction, then you can imagine the soil is also displacing. The soil mass is also huge. And when the soil mass is also supposed to act along with the structure, the amount of dissipation that will take will be larger, and therefore the magnitude of the superstructure self-weight acting in the same direction has nothing to do with it. You are more important to it. See, if you look back at it, vertical seismic effect, when you compare, why is it, the issue is, why does vertical seismic never govern our design? Have you ever thought about it? Have you ever found the vertical seismic governing your design? Whether it is substructure, superstructure? Why? Just remember one thing. The earliest structure that are ever designed, they never designed them for vertical seismic. Earthquake was always treated in the early days of earthquake engineering as a lateral load inertial phenomena. It was never treated. So what does it mean? We have hundreds and thousands of bridges which we built before we understood earthquake engineering better, that it's a 3-dimensional effect, but we never designed for 1 dimension ever. And yet not even one superstructure has ever shown sign of failure. Though we have seen a number of failures in the columns. Number of failures have been column. That means as far as the lateral phenomena is concerned, it's a very real observed phenomena. Whereas the vertical phenomena, observation shows that it is significantly non-governing. Okay, so it has less to do with the what we call it, gravity load direction. But my question to you comes back to it. Why is it that we never see a problem in the vertical direction seismic? The one reason you can think about is the fact that we have no known failure of superstructure under the vertical seismic action. No known failure. Okay, that's one as a data point. Second thing is, if you take a look at the total design bending moment in one superstructure, even if you take a long span one, in long span structure, out of the total design bending moment, how much is dead load and how much is live load? As a percentage. Let us say you're doing something like let's not talk about long span, let us talk about a medium span. Let us say you're talking about a 40-meter span or a 50-meter span. What will be the fraction of the total design moment in the gravity direction which controls the design of the beam? How much fraction will be due to permanent loads? How much fraction will be due to variable loads? Have you ever examined your results in that fashion? Have you ever compared it? Some rule of thumb that used to apply in the early days was for short span, roughly 60%. For medium span, yes. For short span, no, other way around. For short span, live load is more than the bigger component in the total load than dead load. In short span up to 30 meters, it would be roughly 60% live load, 40% dead load. Beyond 30 meters, 30 to 40, it might be 50-50. 40 to 60, 70, it will be something like 60% dead load and 40% live load. And 100 and above, it will be almost 80% dead load and 20% live load. Now comes the question, if on the, let us say you had the full seismic 100% instead of 2/3, what would have happened under certain circumstances, in certain seismic zones? What you would have observed, especially in very high seas. We don't have, please note that as of now, India doesn't have a very high seismic zone. But don't worry, wait for it. 1893 draft version, which I asked you all to read, you will notice that we are going to get peak ground acceleration increase from the current maximum of 0.36 to a maximum of 0.72. Now, if you had something like 0.72 with all the other factors, and SA by G, etc., when you do Z, I by R, importance, response reduction, all that when you do, in vertical direction, you might end up getting something like 0.4, 0.5 as the vertical acceleration. And when you have that, if you have 40% of the self weight, which is at 80%, so you will find that your design bending moment will go more than 100% of your original. Then the earthquake will start governing in the vertical direction. But that's why for small, medium span, because there is no evidence of such a thing happening, that they have gone ahead and prescribed a factor of 2 by 2/3 on an empirical basis.
Sir.
Yeah.
Sir, one more question related to the same topic. Yes, sir. Actually, he's saying like 2/3 of the thing that the horizontal seismic coefficient is taken in the vertical component as a vertical component, but still we are having the time period TV.
Yeah.
It's calculating using
time. See, what he's not telling. What I'm trying, what you have to understand is the response spectrum is derived as a single degree of freedom. It doesn't understand. It doesn't understand what is the stiffness at all. It has been normalized for stiffness. When you do the time period analysis, you consider the stiffness in each direction. You consider the stiffness in vertical direction when you're calculating the time period. So at that time, if you look at it, what you end up getting, the time period for vertical seismic will be very small. Let us say to reduce it to a real life problem, let us say you have a bridge which has about a 30-meter tall pier, so that the pier is reasonably flexible in the transverse direction. For this bridge, and let us say it is supporting a 40-meter span. For this bridge, because of the flexibility of the pier, for the transverse direction analysis, your natural time period might be something like say 0.8, 0.9 seconds. But in the vertical direction, the same 30 meter is very stiff, for which you will get a natural time period of the order of say 0.3, 0.2 seconds. It will only depend upon the flexibility of the beam, which is a simply supported beam. Correct? Its natural period is calculated differently. The foundation, stiffness doesn't come into the picture at all. So then what happens is, for the natural period of the beam, you have to calculate from the response spectrum what is SA by G and take 2/3 of it. It doesn't say take 2/3 of the horizontal in a strict sense, because time period will be different. Because you don't use the same time period which you have calculated for transverse for the vertical seismic.
Okay, sir.
Anything else? If you take a look at your IRC SP 114, you will notice that it is asking you to go do the free vibration analysis of superstress using standard structural analysis software. Okay. And seismic zone factor, please understand, it doesn't say, it only says seismic zone factor for vertical ground acceleration may be taken as 2/3 of that for horizontal motion. What does it mean? It says modify Z. Okay, let me share the screen with you for ease of. Can you see my screen? Yeah, so this is the clause regarding, if you see the thing, vertical component, and if you notice, this is IRC SP 114. So what does it say? It says find out the time period for a fundamental time period for a simply supported. They have given you a simple formula, just like they have given you for the lateral for a single degree of freedom. So you calculate this is for a beam, this is for a beam. After you have done that, what it says is the seismic zone factor, you make it 2/3. So what do you do? That means wherever you have your formula SA by G into Z by 2, I don't know where that formula is, above possibly, before this. No, after this. This zone factor, na? This zone factor, they want you to take 2/3. Okay. Why are they reducing the zone factor 2/3? Because of the fact that the magnitude of energy that is dissipated in the vertical direction is smaller than the energy in the two other directions, as observed by in the large number of earthquakes that have happened in the world. That is why they are saying the vertical peak ground acceleration in the vertical direction itself, you take 2/3. They are not telling calculate for horizontal and multiply it by 2/3. No, that is not what the code is telling you to. It says calculate in the vertical direction itself, but take the zone factor to be 2/3 of that for horizontal motion. I hope the confusion is cleared now. Okay. All right. Anything else for the day? If not, then we meet 4 o'clock next Friday. That is 14th February. All right. See you then. Good night.
Good night, sir.
Thank you, sir.